Yeah, sorry, it was muted. I'm very sorry. Hopefully you can hear me now. Oh, well, okay. Let me know if you can't hear me. Okay, so to get some intuition first before we dive into the formalism, let's look at some slides. So just as illustration, let's imagine we are doing 1D function interpolation. So we have some unknown function f of x as input function of x, and we currently know 2 points on this function, those 2 green dots, right? And now we want to know, okay, what's the function value at this point? And then, okay, what do we assume, right? Well, the first thing you learn essentially is to do linear interpolation, right? But why do linear interpolation? I mean, what's the fundamental reason why the linear interpolation would be better? Well, you can do spline interpolation. That's effectively assuming that it has some polynomial shape in between. So okay, we could do linear interpolation, but why is any such choice special? I mean, the function could take any weird form in between those points, and we don't know which. So that's the general problem, and since we are being uncertain about something and we are patients in these lectures, we are going to use probabilities to express our uncertainty or our degree of belief about what's the correct function value at this point in between. So we need to make an educated guess for this value f at a given x. So imagine we had 3 input points like this, x1, x2, x3, and we were then faced with 3 unknown function values at those points. And I'm just going to call them f1, f2, f3, is corresponding to x1 to 3. Okay, we want to use probability to express our beliefs about this. We could, okay, we need to express some priors before we know any data. So we could do that as just expressing 3 completely independent probability distributions that happen to look like this. Okay. But if they're independent, that means we will not learn much about the function at other points if, okay, what I'm trying to say is this. If these probability distributions are completely independent, they factorize, that means that if you tell me now the true function at point x1, okay, then my posterior at that point collapses into a delta function in this case, unless that data point had some uncertainty. But that tells me nothing about the function at any other point, because these probability functions were completely uncorrelated. And of course, we rarely think that, I mean, most functions we work with are such that if you know the function value at an x point, then you know at least something about what you expect about the function value at points nearby, right? So what we need is that we need to formulate a joint prior. So say we have a joint prior P of f1, f2, f3. Then if we now learn the function at one point, that actually changes the probability distribution at the other points, right? Because then our probability distribution for those other points, we can express that as the conditional. What's the probability of f2 and f3 given this new information about f1? And those are then conditional distributions that have changed. So this looks like an interesting setup, right? Because now we can learn stuff about functions at places where we don't have data.
So imagine you would not just know, for instance, f1, but also the first derivative of f at x1 would like probably model the correlation by means of a Taylor expansion, right? As in, I happen to know what the situation is at x1, and yeah, just well, again, linearly interpolate to the next one, right? I mean, interpolate in a correlation sense this time around.
Yeah, let's say it like this. If you also happen to know the derivative,
yes, yeah, exactly.
at that point,
exactly, yeah.
but that's then certainly useful information that you probably can make use of. I mean, exactly how to correlate these probability distributions, that is the art of GP's modeling.
So that's again a hyperparameter then in the end.
It would, yeah, these we will use correlation functions to express how these PDFs are correlated. And those correlation functions come with parameters, and those will be our hyperparameters in the end. But then you can imagine, okay, now do this, just squeeze our delta x together. So we have many PDFs like this, and we have it. So we're moving towards an infinite dimensional joint prior. And that's the sort of intuition about GPs that, okay, or about not GPs yet, because these are completely arbitrary PDFs, but you see that we're moving towards a prior on function space, effectively, by now squeezing delta x closer together. And from such a prior, right, we could sample possible functions. So we can get a generative model where, okay, like I can sample x points from a PDF, I can now sample functions from this, or function shapes from this joint prior. So this sort of the ideal solution in a Bayesian sense to an interpolation problem would be something as general as this, like take all your prior knowledge about the problem, about what sort of, do you expect a quadratic function, do you expect the function to have a sort of increasing, decreasing trend, all sorts of information expectation you have, incorporate that into a joint prior of any form, right? And then, okay, you perform the full calculation, or someone tells you the true values at some data points, and then for any other x points, what we'll typically refer to as test points, then you can get your best guess for that function value by looking at the conditional distribution. And the problem is that by trying to do this with arbitrary PDF forms is intractable. And this is where we get to Gaussian processes where this actually gets tractable. So yeah, the first step is just the definition of the Gaussian process, as we discussed, an infinite set of variables such as any finite collection has a joint Gaussian PDF. And as we'll get back to, I mean, being a Gaussian PDF, it means that all you need to define them is you need the mean value in each direction, in each dimension, and you need the covariance matrix that defines the covariance between all pairs of variables. And we'll see that we'll choose these sort of indirectly by choosing a mean function and a covariance function. And it's in the covariance function that eventually our hyperparameters will enter. And what this means is that instead of starting from any type of joint PDF or joint prior, we will require that joint prior to be a Gaussian. And if you start from a Gaussian like that, that means that by marginalizing, if you want to marginalize out some of the function values and just look at others, then that marginal distribution will be a Gaussian. If you condition, as we will do, as we go from prior to posterior, we effectively condition our distribution on some of the function values that we now know. And that conditional distribution is another Gaussian. So the Gaussians are sort of a closed family in that sense, that you start with a Gaussian and you get a Gaussian. And that means since the Gaussian is defined by the mean and the covariance, that means that there are analytical expressions that takes, okay, this was your mean and covariance for the prior, here's your mean and covariance for the conditional distribution or the marginal distribution. So suddenly, this problem of working with infinite PDF becomes tractable because we're only using finite subsets and we're restricting it to the Gaussian case. Yes, so this picture there on the right is sort of the classic picture of GP regression, where say the functions on the top there, those are samples from your prior on function space, and here the black band and the gray band is just your prior mean and plus minus one standard deviation. And all these colored functions are example functions drawn from that prior. And then the bottom is the posterior, once someone has told you the function values at some point. And then you see, okay, you can draw sample functions from that posterior, but often you don't see the samples, right? Often all you see is this black band and this, not this black band, and this gray uncertainty band. And this is one of the nice things here, is that this framework gives you sort of local regression uncertainties, in the sense that at any test point, you get a mean prediction, so the black value, and you get a standard deviation, which is the uncertainty band. So you see, as you move close to points that we know, the red points, the uncertainty shrinks. And when we're in the middle between points we know, so far away from data, then our uncertainty is large.
So that means we could also use this information about the uncertainty to compute new ground truth samples in the end, right? So if we happen to know that, well, in between the uncertainty is rather large, and we want to narrow it down in that particular area, we could run the simulation against the statistic and then insert another from there.
So one of the things that this is used for is exactly that sort of thinking, which is was often referred to as Bayesian optimization, which is essentially saying if you can control where to measure the new data point, if X, for instance, was different measurements you could go out and do, then this would tell you, okay, what measurement should I do next to learn the most? Well, I should do it where the uncertainty is the most. So you can couple this with a sort of a loop like that always picks the most optimal next point, which is a very interesting general problem. Okay, so that's our condition. And now we need to get down to the nitty-gritties. And of course, these examples were all one-dimensional, but in general, this will be, the input space will be n-dimensional. And you can also have, the function can also have multiple outputs. So it doesn't have to be a one-dimensional output, even though in all my examples, I will imagine we have n-dimensional input and we have one-dimensional output. Okay. But our basic tool for this, our basic building block, let's say, is the multivariate proportion. So we will repeat a couple of sort of key things to remember about this. So let's do a refresher. Basic concepts that is important so that we don't get confused as we go on. So first, some completely general concepts that are that aren't restricted to Gaussians at all. Just to get some definitions down. So we need to remember that the variance is defined as, so the variance of some unknown variable x is the expectation value of x minus the mean of x squared, where the mean mean of x is just, of course, the expectation value of x. And the reason why we want to be clear on this is because one of the key quantities that we will discuss a lot is covariance. So the covariance, and the covariance is then always of a pair. The covariance is then defined as the expectation value of x minus mu x, y minus mu y. And there's a couple of properties to note. Of course, then the covariance of x with itself is just the variance of x, and also the covariance function is symmetric under change of input arguments. So the covariance of xy is the same as covariance of y x. And of course, we will often use the sigma notation. So sigma x is just square roots of the variance, or what we'll often call the standard deviation. And we will often say that variables are correlated. And technically, what we're talking about is the correlation coefficient, which is typically denoted rho. So let's do rho x comma y, and it's just effectively a normalized covariance. So it's the covariance of x and y divided by the standard deviations sigma x, sigma y. And that means that this correlation factor lies between -1 and 1, and it's of course also symmetric. So we have variance, we have covariance, we have standard deviation, we have the correlation coefficient, and this brings us to the covariance matrix, which is probably the most important beast in GPs. So this is the matrix with the covariances of all pairs of variables. So let's write down the 2D case. So I'll typically use capital sigma for the covariance matrix. So if I only had two variables, this would be covariance of x with itself, covariance of x, y, covariance of y, x, and covariance of y, y. And we could spell this out. In this case, this would be sigma x squared. Here we would have the correlation coefficient x comma y times sigma x, sigma y. This would be the same because they're symmetric. So rho x, y, sigma x, sigma y, and this would be sigma y squared. So because the covariance function is a symmetric function under interchange of input arguments, that means that the covariance matrix is a symmetric matrix. And of course, this might look stupid, but I think it's just useful to see. Of course, the one-dimensional covariance matrix is just the variance. And the reason why I think this is sort of useful to see is that we will need the determinant of the covariance matrix, which will just denote like this. And this is then often called the generalized variance. So we need even in the case of a many-dimensional PDF, we want a single quantity that sometimes should sort of express what's the number that denotes the variance of this multidimensional PDF. And that will be the determinant of the covariance matrix. And you see in the 1D case, that just becomes the variance, as you might expect. So sort of, at least in that limit, it makes sense to call this the generalized variance. So this will effectively appear as a normalization factor in many places. So those were the all these definitions had nothing necessarily to do with Gaussians. So oops. So now let's do multivariate Gaussians. So first, let's actually write down the proper definition of a one-dimensional Gaussian. So I'll often use the notation n for a normal distribution, and then it's quite common to leave out the variable that is actually a PDF for, which is somewhat confusing, but I'll do it still. So this is a PDF for x, but it is a normal distribution with parameters mu and sigma squared. And then, of course, you all know that you can write this as 2 pi sigma e to the minus x minus mu squared divided by 2 sigma squared. But let's write this again in a slightly more suggestive notation. So we can write this as the square root of 2 pi to the first power, then sigma squared. And we can write the exponent as minus 1/2 x minus mu 1 over sigma squared and x minus mu again. And the only reason I write it like that is that if you remember that form, then it's easier to remember the multivariate generalization of this. So let's look at the n-dimensional Gaussian. So that's now a PDF for a n-dimensional vector x. And that will be a normal distribution that now has a mean vector. And instead of lowercase sigma squared, it has a covariance matrix, uppercase sigma. Notice that the notation is then typically that uppercase sigma sort of corresponds to lowercase sigma squared. So sigma here contains variances, and variances are standard deviation squared. So then this generalization then follows the same form as above. So then it's 2 pi to the nth power. And it's now the generalized variance, so the determinant of the sigma matrix. And then it's e to the power minus 1/2 x vector minus mu vector transposed. And then the inverse of the covariance matrix, and then x vector minus mu vector again. So you see this as sort of the same form as the 1D distribution I wrote now. And we will, the last thing we'll do to sort of get our intuition right for multivariate GPs is that we will write this out in the 2D case and just draw two 2D Gaussians to see how these different parameters affect the distribution shape. So say for to the case. So now let's do x1 and x2, because that's how we'll use xi generally. So that's now a normal distribution. It has a u1, u2 vector, and it has a covariance matrix. And if you write this out in all its glory and make various simplifications, you get that this is 1 over 2 pi sigma 1 sigma 2, and you're left with 1 minus rho squared. So rho squared is now, since we only have two variables, we only have one correlation coefficient, so that's just rho. And we get e to the minus 1 over 2, 1 minus rho squared. And then we have a long bracket that contains x1 minus mu1 divided by sigma 1 squared. It contains x2 minus mu2 divided by sigma 2 squared. And importantly, it contains the cross term, which is 2 rho x1 minus mu1 sigma 1 x2 minus mu2 sigma 2. Yes. So this is the 2D case, and we notice that for rho goes to 0, then P of x1, x2 goes to just to a factorized PDF, because then the cross term vanishes and you're just left with a product of two normal distributions and two one-dimensional normal distributions, mu1 sigma 1 and mu2 sigma 2. And if instead, so remember that's the correlation coefficient has to be within -1 and 1. So if you take the correlation coefficient to its extreme value, one of its extreme values, joint distribution P of x1, x2 gets, let's say, squeezed onto the line. So then the distribution narrows down and ends on the line through x1, x2 space. And that particular line is given by x2 and then the sign of the correlation, sigma 2 over sigma 1 x1 minus mu1 plus mu2. So this is just a straight line through x1, x2 space that this distribution collapses towards once you make x1 and x2 perfectly correlated. So let's just draw two quick examples to get our intuition. So first I'll draw an example that of two variables that are very weakly correlated. So let's say I have my mu2 here, I have my mu1 here. And what I'll do is I'll just draw a contour of constant likelihood, right? And then you have to picture a Gaussian on top of that. So, okay, we have a center here. And okay, I want it to be I don't know. Okay, that should have been in the center. You get the point. So this would have a correlation. Actually, So let's do that again. Oops. Probably show it again. So this would have a correlation coefficient that is negative but fairly close to 0. And at least I meant for this slope to be fairly close to 1. So the slope will be given by the ratio between sigma 1 and sigma 2 and sigma 1. So I meant for these to be weakly correlated, so it's a blob, but still the direction of the blob is like a false with as -1. Whereas if we instead did say something like this, and say solution something like this, then these would be positively and very strongly correlated. And in this case, the slope is less than +1. So this would be less than 1. So that's sort of, okay, that's the intuition of how, at least in the 2D case, the covariances here are parameterized in terms of the correlation coefficient, and in the individual variances sets the shape of the distribution. And that was the first part done. So let's stop there and take 15 minutes. Okay, so this was, now we hopefully have some intuition for how multidimensional, at least some intuition for multidimensional. Now it will be notation bonanza for the next 10 minutes at least. So now we'll actually get to GP regression, and we'll start by finding a bunch of notation. So I will, in my notation, I will assume that the input space is n dimensional, and we have n training points. I mean, always found almost in the context of GPs, always found the terminology of training almost misleading, because it's just, okay, the number of points where you know your function. And the only reason, as we'll get to, the only reason why you have to do some sort of quote-unquote training is that your covariance functions or kernel functions will have hyperparameters that you need to fix. But I mean, if that wasn't the case, we would just, okay, we have made a Gaussian assumption. Here's our known points, and let's get the marginal distribution for view points. But anyway, we have n training points, each live in an n-dimensional X space. So X vector is input points in this and in space. And that means that, yeah, and then f of x vector is the, in principle, unknown proof function at x. So this is in our f space, our target space. So x is feature space, f is target space. Then x vector I is then an input point where we know the true function value. So that will be one of our input training points. And just as a shorthand, we will say that fi is, by definition, f at one of the known training points. So that means that we could think of our total training set as just the data, d, and that would then be the set of all our input points, x vector I, and the corresponding target values fi, where I here runs from 1 to n. So that's our data, our training sets, and we will need yet more ways to represent this. So we can take all our n input points, each living in n dimensional space, and we can put them in a matrix, an n by n matrix. So that will be capital X. That will be, if each of these input points are row vectors, it will be that's n. So this is n times n matrix with all let's say input components. Training set. And to go with that, we can say that we have an f vector, which is then the known function values f1 to fn. So we could also say, can also say that our total training set is just this capital X matrix and f bar matrix. And so these were all the training points and notation for that. And then we want to estimate the function value at some new input points. And this new input point will denote by x vector star. This is test point, a point where we estimate the unknown f star, which is per definition f at this test point. So that's the notation we will use. And our starting point is to formulate the joint prior. Start by or start with a joint prior, and then for all, let's call them relevant f values. So you start with a prior that describes for all the f values, both your training data and your test point, because this is sort of prior to actually looking at those function values that you know. So this will be the joint prior distribution for f bar and this single point f star. And what we will assume is that we will assume that you always know the input coordinates. So you're never uncertain about the input points, you're just uncertain about the function values at those points. So even though this is a prior, this will still be conditional on your input points. Of course, if you actually have uncertainty also in the x direction, this formalism could get a little bit different. And notice that this is now an n+1 dimensional PDF. F vector is n-dimensional and f star is 1 extra dimension. Since we implicitly say that we always know the input points, we could also write, just put that in bracket, could also write this as PD f star, where this would just mean, okay, it's our prior for our training data and our test points, where the X matrix in D would just belong on the other side of the given on the conditional. I'll typically spell it out this way. So now, of course, we require this prior to be Gaussian. That means to specify it, we must specify two things. First, n+1 dimensional mean vector. And this mean vector now contains mu1 to mu, now it says mu f1, that's mu fn, and at the bottom it also contains mu f star, or mu for f star. So we need our n+1 dimensional mean vector, and we need n+1 times n+1 covariance matrix, right? Because this is a multidimensional and n+1 dimensional Gaussian distribution. If we just specified all those numbers, all the numbers in the covariance matrix, then we would have a fully specified prior, and we could then condition it and get our posterior, a fully specified posterior distribution for this f star value conditioned on all the known training points. But then that would be specific to that single input point x star, right? So what is typically done is that you don't choose all these numbers directly, but you choose a mean function as a function of input point, and you specify a covariance function or kernel function as function of input points. And you use those to define your mean vector and your covariance matrix. So do this, let's say, indirectly by choosing a mean function. So that will be mean function of form m of inputs and a covariance function, also referred to as the kernel. So we use k, and being a covariance, it has to have two inputs. So just use x and x prime as two different input ones. But so that means, I mean, the definition of these is that, of course, m of x vector. So the important thing here, and this is something that often confuses a lot of people when they first encounter GPs, is that the mean function and the covariance function, right, they are functions on x space. But the values of these functions, even though it's the kernel function of x and x prime, it's not the covariance of x and x prime. The value represents the covariance of f of x with f of x prime. So the values represent mean and covariances in f space, but they're functions of input space. So that means that m of x, what this mean is that it's the expectation value for this function value f of x, which means that, of course, since it's a expectation value, it's f times a probability distribution for x df. So integrated over all possible f values f of x point. And the covariance function with inputs x and x prime has now the expectation value of f of x minus the corresponding mean times f of x prime minus its corresponding mean. So again, mean values and covariance values in f space. Right. And so choosing to define a GP, we'll have to choose a mean function, we'll have to choose a covariance function. As it turns out, the choice of mean function is typically not so important. The choice of covariance functions is very important. But assuming that we have specified this m function and this k function, then our joint prior is now this. So our joint prior, and by joint prior I mean then the prior for both f vector and f star. So this was p of f vector f star given all the input points and given the input test points. And this is now a giant normal distribution. I'm going to write it as a giant normal because I need some spacing. So the mean vector, right, is now, we'll write this as m of the matrix x. I'll explain all this notation, though it's probably mostly self-explanatory. So the upper part here is the mean for all the training points, and then the lower part is just a single value, your prior mean at the test point. So that was the sort of mean vector, and then we need a covariance matrix. And this covariance matrix we'll write as, first of all, so this big covariance matrix is n plus 1 times n plus 1. But we'll write this as first in the upper left corner an n times n matrix, which is the covariance matrix of all your training points. then we'll have a vector, which is the covariance function, taking as input this X matrix and this single test point. And down here is just the reversed order of arguments. And then down here is a scalar, which is just the covariance function at the test point with itself. So just the variance, your prior variance at the test point. So the notation here where this M of the X matrix, what we mean by that is M of X1, blah, 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 down to M of Xn. And sigma is the covariance function taking as inputs the matrix of all input components in the training data. So this will be K at X1, X1, blah, 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 up to K X1, Xm. Down here, we'll find K Xm, Xm. And this is symmetric, of course. So we had M of X, we had sigma, and we need to define what we mean by K of X matrix, comma, X star test point. And what we mean by that is this vector, K of X1, comma, X star, all the way down to K of Xm, comma, X star. And finally, if I reverse the arguments here, what I mean by that is just the transpose of that previous vector. So it's the notation, again, the notation gets so heavy, but it's effectively just trying to summarize a n+1 times n, no, an n+1 dimensional Gaussian distribution. Any questions about notation? If not, then we can actually get some predictions out of this. So if we assume that we have a fully specified M function and a covariance function. Our goal is a predictive posterior distribution for the unknown F star. And we get that from quote unquote just looking at the data we had. So get it from the conditional Pdf, P of F star, and now conditioned on the known function values, F vector, and X matrix, and still the input points. This is now a one-dimensional Pdf. And because we restricted ourselves to only working with Gaussians, we know now that this conditional PDF will also be a Gaussian, and we have analytical expressions for its mean and variance. So I'll not derive those expressions, but you'll find them in the appendix of this Rasmussen and Williams book. So this conditional PDF is a Gaussian with okay, let's say a Gaussian. So it's P of F star given F vector X matrix X star. This is now a one-dimensional normal distribution with parameters that we'll call mu star and sigma star squared. And we know these where mu star is the mean function at your, or the prior mean function at your test point. So that's, so the equations I write down now are effectively the key equations of GP regression, because these are actually our predictions. Mu star is our prediction, our central prediction, and sigma star will be our regression uncertainty. So this mu star corresponds to the black line, right, in these plots. So you're saying your central prediction will be the central point of your prior, which is just M star, and then it's shifted by this term. So it's K of X star comma X matrix, and it's the inverse of sigma, and then there's a bracket with F vector minus M of have I gotten the notation wrong there? Oh, 2 seconds. No, it's fine. Right. So, and so this is effectively our, let's say, point estimate or point prediction for F star. And we'll discuss that correction term or the shift in a minute. So this was mu star, and then we have the uncertainty in our prediction, so sigma star squared. And that's just the variance, our prior variance at the test point. And then a reduction of variance of uncertainty, which is this term, K of X star comma X inverse of the sigma matrix, and K of X matrix comma X star test point. This is our prediction uncertainty or variance. So I will, for once, use a color and score a frame around this, because these are, or slight variations of these are the key equations. So let's try to just get some sort of intuition for what these equations actually mean, or what they say. So first of all, your central prediction is mu star. What it says is that, okay, you start from your prior mean, M of X star, and then you shift it. You shift it by a weighted sum. So the last last term there, right? What that is that it's taking your m of x is your prior means on all the training points. So what you expected the training point to look like before looking at the training points. The function value, that's your m of x. And then it takes the actual true values at the training points. Those are the f vector. So it's effectively taking a vector that just measures at every point in my training set, how much was the true function shifted from my central prior expectation. So it's looking at the shift from away from the prior, or the central prior, and the term before that is effectively measuring for each of those points in the training set, how correlated do I expect that function value to be with my f star, right? So if I expect my f star to be highly correlated with training point f4, then if f4 was shifted a lot away from its prior mean, then I will expect my f star to be shifted quite a lot from the prior mean at x star. So it's taking your prior mean at x star and shifting it. And how is it shifting it? Well, it's shifting it sort of by learning how all the other points have been shifted and looking at how correlated are all these other points with the point I'm interested in. That's the intuition. At least that's my intuition for what this expression means. The variance is, so you're starting with, so remember that variance is always a positive number, right? So you're starting with just the variance of your prior. So this is k x star x star. That's just, okay, what's my a priori uncertainty at this x star point. And then that uncertainty has to be reduced. It can only be by the information that you get from other parts of the function that will make you more certain than you were in your prior. So that's, the variance will be reduced, and that's the reason for the minus sign. Oops, this was a mistake. And so it's reduced in proportion to how much information all the training points contain about the function value at the point you're interested in. And how much information they contain is just only depends on how correlated you expect them to be, right? So if, and this again goes all the way back to the sort of the slides we were looking at, right? If we say that two function values are completely uncorrelated, then so x star and x10, and if I say that the function values at these two input points are completely uncorrelated, then learning the function value f10 tells me nothing about f star, which in this expression means that f10, that information will not reduce my uncertainty anything. Because in that case, that will be a term in this second part, which is just 0. So the more they're correlated, the more the training points, the more they're correlated with your test points, the more they bring down your uncertainty at the test point. That's my intuition, at least, for how this works. It's also worth noting that in both these expressions, we need the inverse of this covariance matrix sigma. And that turns out to be the sort of main computational challenge of GP regression, is that this inverse pops up everywhere. So, because in general, finding the inverse of a matrix, in general, computing the inverse of an n by n matrix is an n cubed operation. And remember that n in this case was the number of data points they have. So this is effectively the reason why, as we'll discuss in more detail, this is the reason why the sort of naive implementation of GP regression scales badly with too high number of data points. But so if we repeat prediction at many different X star points, we get we can construct a familiar GP style plots, right? Which would be here's X, here's f of X, here's some known points, and at every other point here, I have computed the prediction, mu star, and some corresponding uncertainty band. Like that. So that's how those plots arise. A very important point, this is also a source of a lot of confusion. The facts that are prediction for the unknown function values are given in terms of probability distributions. Of course, does not imply that the function is indeterministic. It does not imply that sort of repeated evaluations of the true function at x star would give different values. The true function might be completely deterministic. There is one true function value out there, but we are just expressing our lack of information about it using a probability distribution. The reason why this is confusing is that traditionally one of the ways in which GPs are introduced is in the context of having noisy data. So you have data where that you think are, okay, there is some underlying true function, but then my data points are some sort of noise, have some noise on top of that. And in that case, of course, sampling the sort of data at the same X value over and over again would give you varying data points. So this is a source of, I think, a lot of confusion. And we will, but for now, we have looked at the noiseless case. Right? Our training data contains the true function values, and we'll see what changes if we add noise. Effectively, what you need to keep in mind is what exactly am I predicting? For now, we have looked at the posterior, which is always a posterior for f star, and where f star is the true function value. But imagine that you had a model for the data which was something like this, where, okay, so this is just saying that, okay, there is a true function f of x, but my data y are true function plus some noise. And this noise epsilon is a random variable drawn from a Gaussian with zero mean and some noise level, same one, right? If this is your model for the data, then you can get, either you can have a GP that has this form. Now your training data are y values, not f values, because you don't know the f values. So you need to keep in mind whether you're looking at this or you're looking at That's going to be y star. So the first one would be, here's my degree of belief for the true underlying function at the point x star, when all I have is noisy data. The other GP would be, what's my degree of belief for the sort of, if I were to sample a noisy data point at x star, in what range do I expect that data point to lie within, given my existing noisy data? And these are two different things. But it's very easy to go from one to the other, as we'll see, but they're conceptually different. So I see that we won't be able to finish, which means that we will have one more lecture on this, but that lecture will probably be shorter than might just be a 1 hour lecture. But now we get to the tricky part, right? Which is actually choosing the kernel function. Choosing and optimizing. I tend to try to rather call it a covariance function because that says more about what it actually is. But of course, we're just talking about kernel. And this is what is doing is choosing our prior. So by choosing our current functions, we choose our prior over function space. And so this choice should encode all our sort of expectations about the true function. So our prior on function space. So kernels encode information about, for instance, the smoothness of your function and the typical length scale. So do you expect, do you a priori expect your true function to have a lot of short wiggles or very like short length scale or long length scale? It encodes things like, do you expect your functions to have some sort of periodicity? Is there some sort of trends? Is it increasing, decreasing in some way? Is your function symmetric in some way? Perhaps it's symmetric around the origin, and etc. So you're not specifying, you're not saying, as you would in a lot of other forms of the interpolation or regression, saying, I want to use a polynomial of degree blah, or something like that, or I will use a sine function or a cosine function. You're not specifying a parametric form, but you are, through your choice of kernel, specifying your expectations across on the space of all possible functions. So this is the main modeling step in GP regression. The choice of the mean function is much less important because it's typically you're completely dominated by the data and by the choice of kernel function. So often you'll see that this m function of x is just set to 0, or it's just, at least it's very often just set to a constant function. It might, perhaps you just take, here are all my f values, my training point values. I'll just take the average of those f values, and I'll put m of x is just equal that constant value. It's still important to keep in mind that it's there, because so for instance, imagine in this case, that that I had these 4 data points, and then say that my mean function was just a constant at f equals 0. Right? That was my prime mean function. What would happen to my prediction as I move outside the data? Well, in that case, my prediction would drop down towards the mean, right? Or towards the prior, I should say. And it would go something like this, right? So your mean will affect how your function behaves far away from data. So it's important to keep in mind. Okay, I think we'll have to stop there, and then next week will be a tour of kernels, effectively. But it looks like that will be, and a discussion of this difference between noisy and noiseless data. But I'm pretty sure that will just be a 1-hour lecture. Yeah. So let's stop there. And again, apologies for not having published the project yet. It will come today because, yeah, too busy. But effectively, it will just be do a Bayesian parameter estimation or model selection or a GP regression on a data set you choose, and and I will list suggestions for things you should investigate. Okay.